Welcome everyone to today's Explainer. I am absolutely thrilled to have you here because we are tackling one of the most critical macro problems of our time, which is transitioning to renewable energy and doing it safely and efficiently. Today we're diving into a really fascinating case study that uses computational modeling to design a 100 megawatt combined cycle power plant. We're going to look at the whole shebang: the physics, the software, the big triumphs, and yes, the very real engineering frustrations that come with simulating massive thermal systems.
Okay, let's dive right into this. 12.7%. Back in 2018, that relatively tiny slice was all the renewable energy produced within the United States. The vast majority was still completely dominated by natural gas, petroleum, and coal. If we want to change that statistic and rapidly deploy new, highly efficient thermal energy systems, we have a massive engineering gap to close. And closing that gap, well, it requires some serious innovation.
Which brings us to the ultimate engineering quest, right? How do we test new, incredibly complex energy systems without spending millions of dollars on physical prototypes? I mean, building, fabricating, and maintaining a complex power plant by hand just to see if a new design might work is completely redundant. It's incredibly resource-heavy. If the system doesn't function as intended, you've just wasted years and millions of dollars. The answer, of course, lies in computational modeling software. Here is our roadmap for today. 1. The energy modeling problem. 2. Enter OpenModelica software. 3. Mastering acausal modeling. 4. Simulating the Brayton cycle. 5. The Rankine cycle challenge. And 6. Future of virtual energy.
All right, Section 1. The energy modeling problem, the high cost of prototyping.
You know, virtual simulations build this absolutely crucial bridge between textbook physics and multi-million-dollar construction. They allow researchers to test the absolute limits of a thermal energy storage system or a massive power plant entirely in the digital realm. And it's expected that these simulations won't just be for the design phase, but will actually play a huge role in future plant maintenance and real-time day-to-day operations.
Section 2. Enter OpenModelica software, the open-source solution.
For research teams really pushing the boundaries of renewable technology, having a free, incredibly flexible tool that can model across a wide array of applications is absolutely vital. OpenModelica is the open-source tool of choice here. But to understand it, we really have to understand its language, Equation-Based Object-Oriented Language, or EOO. It's a declarative acausal modeling language. Simply put, it allows users to describe massive physical engineering components just by writing out their equations. It essentially transforms complex, sprawling physics into manageable, highly reusable virtual objects.
The workflow for an engineer using this software is actually brilliant. It starts in OM Notebook. That's an interactive tool where you learn the language basics through coding tutorials. Then, you graduate to OM Edit, the main graphical workspace where you can actually build your models, either by writing code or visually connecting block diagrams. Finally, you tap into the Modelica standard library. This is an open-source library packed full of ready-made components for thermal, fluid, and electrical systems. You literally just drag and drop components right into your workspace.
Moving on to Section 3, Mastering Acausal Modeling, the math behind the machine.
This software introduces a completely different paradigm for engineers. With traditional imperative languages like C++ or Fortran, you have to write explicit step-by-step algorithms. Actually, scratch that. It's more like writing a ridiculously complex instruction manual from scratch just to calculate specific variables. It's exhausting back-end work. But Modelica, it's an equational language. It uses acausal modeling. Think of it like Lego blocks. You don't write the step-by-step instructions, you just take the pure physics equations straight from a textbook, drop them into the software, and the compilers automatically figure out the computational solution for you. It is a real game changer.
So the crucial point here is that behind the scenes, these visual components are seamlessly exchanging information using fundamental continuity equations. Imagine our entire power plant as a series of control volumes. Everything is governed by just three main pillars. You've got mass balance, tracking enthalpy and pressure, momentum balance, calculating pressure losses and pipe friction, and energy balance, constantly monitoring the mass flow rates entering and leaving every single component.
Section 4. Simulating the Brayton cycle, achieving the first 70 megawatts.
The strategy to hit our 100 megawatt goal is incredibly clever. The load is actually split into two parts. The Brayton gas cycle is designed to generate the bulk of the power, 70 megawatts. The remaining 30 megawatts will come from the Rankine steam cycle,
By using inverse computation, engineers can essentially work backward from this 100-megawatt goal to find the exact, highly specific mass flow rates needed to hit those targets.
Just think about the extreme engineering data in action here. The model pushes air through a compressor, blasts it into a combustion chamber, reaching insane temperatures, peaking at a staggering 1400 Kelvin, and then out through a combustion turbine. By meticulously mapping the pressure and specific enthalpy at every single state, the virtual system successfully hits that massive 70-megawatt load requirement. And guys, this was a massive win for the simulation. The OpenModelica Brayton model was square, which just means it had an equal number of equations and variables. It successfully flattened or instantiated, and most importantly, it reliably simulated the steady-state power generation. When the equational math perfectly aligns with the software architecture like this, the capability of the tool is just breathtaking.
Section 5. The Rankine Cycle Challenge. Trial, Error, and Frustration.
Now, on paper, the math for the Rankine cycle was perfectly mapped out. The thermodynamic state analysis charted exactly what needed to happen across 6 different states involving 3 heat exchangers, a steam turbine, a condenser, and a pump. The exact pressure, temperature, enthalpy, and entropy were all meticulously calculated to hit that remaining 30-megawatt goal. But despite having all that precise thermodynamic math, the software completely hit a wall. Both the Rankine cycle and the heat recovery steam generator models were unable to flatten. They literally broke during the simulation. Why? Well, because being an open source tool, there are sometimes software inconsistencies and bugs buried deep inside the standard library itself. Troubleshooting this meant diving into open source forums, dealing with broken subassemblies, and navigating the very authentic, very human frustration of computational modeling.
Which brings us to Section 6. Future of Virtual Energy. Moving forward.
It's super easy to look at a broken simulation and just see a failure, right? But we really have to step back and look at the bigger picture. Even with bugs in the steam cycle, establishing a 70-megawatt working simulation of the Brayton cycle from scratch absolutely proves the viability of modeling these complex systems virtually. Remember the fundamental rule here. Encountering a failure in digital code is infinitely cheaper and safer than encountering a failure in a physical steel power plant. This case study is a truly vital stepping stone.
The research perfectly summarizes this whole experience. Modelica's acausal EOO language shows powerful, promising modeling capabilities across multi-domain platforms. I couldn't agree more. Despite the hurdles, the ability to drop raw textbook physics into an open-source software and simulate a functioning power plant proves that equational modeling is an absolute powerhouse for the future of energy innovation.
So that leaves us with one final big thought. As these open source libraries get refined and the bugs are squashed by the global engineering community, what will the next breakthrough in virtual system modeling unlock for the future of our electric grid? We are just scratching the surface of what's possible here. Thank you so much for joining me on this explainer. Keep learning, and I'll see you next time.